Welcome back to my exhaust fan controller project series. In this video, I'm going to look at a few options for measuring temperature. This is definitely not an exhaustive list. There are lots of ways to measure temperature. These are just the ideas I had, and I wanted to share some of my thought process. The software I'm using to present here is PSpice for TI, which is a free version of Cadence that I would definitely recommend checking out. Only as an honorable mention, I wanted to show the DHT11 temperature and humidity sensor. Basically, you just need one resistor and 3 wires to connect one of these up to a microcontroller. They're fairly popular among hobbyists because they're so easy to use, but I'm not going to be using any type of digital sensor in this project. There are a lot of different digital temperature sensors available out there, and they all have one thing in common. You need to communicate with them. For this project, I'm going to skip involving a microcontroller entirely for reasons mentioned in my previous video, so let's just move on to my first analog sensor. Before I get started down this rabbit hole, fair warning here, I'm going to be talking about diodes for a little bit, but none of this will be used in the project. If you'd like to skip this discussion and get to the components that are more useful, you can go directly to the timecode listed on the screen. With that being said, silicon diodes have a very reliable negative 2 millivolts per degree Celsius temperature coefficient. To get this temperature variation to work properly, first you need a temperature-independent current source, which isn't as easy to make as it may sound. If you can hold the current constant, then any change in temperature will result in a predictable change in the diode's forward voltage. I've heard that using discrete diodes for temperature sensing has problems, but since I have some on hand, I wanted to check this out before ordering any other parts. I'm going to measure 2 temperatures and compare them, so that means I need 2 current sources that are precisely matched, as well as 2 diodes that are precisely matched. The current source problem is fairly easy to fix by putting the diodes in series. This way the current through both will always be the same, and I just need one accurate current source. This does make the voltage measurement more complicated because we have to take the difference of voltage across D1 instead of just measuring the node voltage across D1. But it's not really that complicated. This is a basic difference amplifier circuit. The only real problem with it is that it's going to be drawing some current from these nodes, so that some of this 10 milliamps is going to be drawn into these resistors and down to ground, which can cause an imbalance in our diodes. And of course we wouldn't want that, so all we do is add an analog buffer circuit to prevent any current from flowing that direction, and now we have a difference of the 2 voltages, and we can compare our cabinet voltage to our room temperature voltage. I set up this circuit with some 1N4001 diodes that I had on hand. These were all from the same tape, so I'd expect them to be as close to the same as you can hope to get. The supply measures 2.003 volts. RA is 99.7 ohms, and RB is 100.4 ohms. I measured the voltage across D1A as 582 millivolts. D2A was 588 millivolts. D1B was 602 millivolts, and D2B was 576 millivolts. Using the measure values, I calculated the currents through each of these branches. IA was 8.36 milliamps and IB was 8.22 milliamps. As you can see, there's a lot of variation between these diode voltages, and I can't really confidently use this approach to measure temperature. To be fair, I'm told that you can do this better with diode-connected BJTs, but I don't have a lot of BJTs laying around to test. I might have to do that in a future video. For now, I'm going to abandon this idea and move on to something else. A thermistor seems like an obvious choice for this project, and I think it would work very well. They're low cost, accurate, reliable, small, easy to use, and you'd only have to run 2 wires to one for this. Basically, you can just hook them up in a voltage divider like this, and then you can measure the variation of resistance at the output as a voltage. For the comparison voltage, you have a few choices. R3 could be just a resistor of a fixed value, for example 8 kiloohms, and that would be your trigger point. You could make it adjustable with a potentiometer, or you could use another matched thermistor to give a comparison temperature. For my project, I would want to have one in the room and one in the computer cabinet to compare the 2 temperatures. Just as a side note, the op-amp on the right just represents my comparison circuit. We'll get into the exact circuit design in the next video. Thermistors are a great way to measure temperature. In fact, I would have used them in my design if I didn't have an easier option available to me. You could definitely implement the exact same solution I've come up with, but just using thermistors instead of the sensor I'm using. I decided to take a look in TI's portfolio and see what they had available in through-hole analog sensors. First, I went to analog temperature sensors, then to the product parametrics page. I knew I wanted a TO92 package, which is a small leaded package common to low-power 3-pin devices. I figured this would be an easy package to use as a temperature probe on the end of some wires. I also knew that I wanted to use the same 12-volt supply from the fan for my sensor's power supply. So I sorted by supply value, and there were only really two options here. The LM34 and 35 are pretty much the same, but the LM34 outputs directly in Fahrenheit degrees, while the LM35 outputs in Celsius degrees. You could use either, but I decided to go with the LM34 since it will have an output voltage further from the ground rail. As an example, in my house is typically 75 degrees Fahrenheit, which is 750 millivolts at the output of the LM34. The same temperature in Celsius is about 24 Celsius, which would be 240 millivolts at the output. I ordered some samples and I'm going to use these to build my project. For a comparison to the diode test that I did earlier, I hooked up 4 LM34 sensors side by side. The temperature measurements were all within 1.1 degrees of each other. I think 2 of these will work great in my project. In this video, I've just covered some different methods of measuring temperature with analog sensors, including the one that I've selected for my project. In the next video, I'll go into some detail on the circuit design that I'm planning to use and do some simulations to show how it's going to work. Thanks for watching.